All right, let's do this. Hello, my name is Adam Torek, and today for the Quantum Machine Learning Seminar, I'm going to be talking about quantum graph neural networks. So to start out, variational quantum circuits, also known as quantum neural networks, have been useful in solving a variety of problems that can't be solved by or modeled properly by classical computers. Thanks to the properties of those or thanks to the properties of quantum computers, such as superposition, we can use huge encoded, we can essentially exploit the superpositions inside quantum particles using quantum supercomputers to immensely speed up processes. Another thing we can do is use the properties of quantum superpositions to efficiently fit quantum circuits to given data. And another thing that's relevant to this paper, some background, is graph neural networks. Those have shown all kinds of promises in dealing with complicated graph networks and extracting information from them. Some of the applications have been in physics, chemistry, biochemistry, social graph networking, among other uses. And these are only scratching the surface of the many uses they have. So the writers of this paper thought to themselves, wouldn't it be a great idea if we took quantum neural networks and embedded them, or took graph neural networks and embedded them into a quantum space that quantum neural networks can learn in order to leverage the inherent properties both have to solve even more complicated problems. And enter today's paper, quantum graph neural networks. So as some background, before we get started, graphs are data structures commonly used in computer science and machine learning. They're used to represent all kinds of complicated data. And they're able to do this by using a deceptively simple system. By modeling linked data using vertices and edges, where the edges between the vertices represent links between nodes, and those nodes can be anything. We can represent all kinds of information from machine networks to social networks to chemicals to quantum states and everything else. If it can be represented by a graph, it can be held in this structure. And these systems can also, in computers, they're usually stored as adjacency lists or matrices. The matrices, by the way, are just store links between edges. So if there is, the matrix is organized with the number of links on one edges on both sides, so it's a square matrix. And if there is an edge between two nodes in the matrix, or in the graph, it's put as a 1 or a weighted value, and when graphs have weighted values on the inside the matrix. Adjacency lists work in a similar way, where you have a list of lists and each node has a list of the other nodes it's connected to. And graphs can have all kinds of properties in them. They can be directed or undirected. They can also have weights between the edges. And they can also have other properties as well. And in this paper, they use adjacency matrices to represent these graphs so they can be put into a quantum space and operated on quantum variational circuits more efficiently. So yet more backgrounds. Neural networks are a kind of special machine learning system that is built on top of perceptrons, which are basically represented by an activation function of your choosing. And they take in inputs with weights and output an activation signal with a bias term on it. And these neural networks learn by adjusting these weights and biases when they make predictions. So the neural networks become have hidden layers basically when there's a layer between the input and output layer. It's called hidden because you can't necessarily understand what's inside of them. And these perceptrons hidden inside that hidden layer of the neural network can learn correlations in a given data set that aren't obvious. And these neural networks are very powerful because each individual perceptron inside them can learn different features of the data, and that can all be combined together into a single output. And this property has been leveraged extensively in quantum or in graph neural networks, which often take the graph representation space and put it into a space that a neural network can learn from. What these neural networks do is they take in graph inputs and output graph outputs, but usually, and the training regime of these neural networks is built in such a way that the output graph is transformed in a way that corresponds to the task the machine or the neural network is learning. A very popular way of representing these neural networks or having neural networks learn graph data is by using graph convolutional networks that are trained on the adjacency matrix representations of graphs. And they use convolution layers to actually learn the features inside these graphs. And what's unique about this is the convolutions work in such a way that they are permutation invariant, meaning that when you swap the nodes inside of a matrix of a graph, the convolution layer can learn it as if it's the same graph, essentially. So it can handle different changes inside the adjacency matrix. And that's what makes graph convolutional networks so powerful. And some of them also learn on spectral features based on the graphs, which essentially take the adjacency matrix, project it into another linear space, and the model learns in some ways off of the adjacency matrix and the projected matrix. Some models choose one or the other. Some models choose both. In the case of this paper, they chose both. And one more piece of background before we finally get to the paper itself is about quantum operators. The writers and researchers of this paper used the Hamiltonian operator, which is a special operator, and these operators work on the wave functions that represent the probability space of quantum particles. So you can think of the wave function as a sort of a function that defines the probability distribution of where you'd find or sample an individual particle. And in quantum mechanics, they use the Hamiltonian operator to represent the energy of a quantum system using this probability distribution system. The Hamiltonian operator has a kinetic and potential energy component. And each of these components focus on a particular part of that energy equation. And these are often used with the Schrodinger equation to actually solve or model quantum systems. And these systems can also, the Hamiltonian operator, long story short, essentially allows us to model the distribution of energies inside quantum particles and quantum systems, which is important because this is a key part in the methodology of their paper. So what the researchers here do is they construct a networked quantum system where they have each node in the graph represented by its own quantum circuit. In this paper, they use qubits, but you can represent these nodes inside the adjacency matrix using multiple qubits, entire quantum computers, or even multiple quantum computers chained together. And this was one of the breakthroughs of their paper was the ability to model each node and the properties between them using an arbitrary size of input, or arbitrary size of quantum computer. And the quantum circuits they used single qubits. And another clever thing they did was they took the Hamiltonian operator and essentially made it the loss function of these quantum variational circuits. What they do is they'd sample the energy state, and the energy state would represent, using these network quantum systems, the actual properties of the graph, and more than that, the properties of the actual quantum neural network, graph neural network is learning. And they'd essentially use use a quantum system's tendency to decrease overall energy as a way to fit the space of the quantum area they're trying to model, in the case of quantum graph neural networks. Very clever advancement there. And using this system they built, they proposed 3 different graph neural networks. They proposed a recurrent quantum graph neural network for modeling time series data, especially for quantum systems. They proposed a quantum graph convolutional neural network to represent adjacency matrices of graph convolutions between their qubits they were using and between their node representations. And they also applied a spectral transformation, which used a special kind of Hamiltonian that would model the projected spectral graph that, I don't know how to quite put this into words. They basically encoded the quantum computer on the data like with the convolutional neural network, but then they applied an extra step that projected that quantum state into a smaller quantum state that their spectral quantum graph convolutional neural network could learn on. And for their experiments with these 3 proposed models, they tested their models on 4 different quantum problems. And they wanted to see if the representation using their specially designed quantum graph neural networks could actually fit these spaces. So in the first experiment, they modeled time-dependent quantum dynamics using their recurrent neural network. Recurrent, by the way, means that each node inside each part of their quantum graph neural network has an edge that goes into itself. So it can learn time series data where you have I'm sorry, this is a complicated paper. They were very ambitious with this. They took all kinds of quantum parts and put them together. The paper itself is very technical. I'm already skipping over a lot of details even now. And in their first experiment, going back to that, they used the recurrent features of their special quantum circuit to learn time-dependent quantum dynamics. And in their second experiment, they used quantum convolutional neural networks to model quantum sensor networks, in which they essentially use the QNN to detect, or QGCNN to detect changes inside a quantum system. In their third experiment, they did unsupervised graph clustering, where the quantum circuit basically represented learns connections between nodes and would use differences in the types of connections it found to classify each kind of graph. It was a pretty clever setup. And they were able to do this by using by doing their spectral, or using their spectral model. And in their fourth experiment, they would detect graph isomorphisms using their convolutional graph neural network. And the experiment results were pretty surprising. They were able to extract a good amount of information from all 4 different quantum experiments. The first showed that their quantum neural network could fit time-dependent quantum systems pretty accurately. Their second experiment basically hit the limits in their sensitivity that the model could have for that problem. So in other words, it could detect the smallest changes or smallest quantized changes in that system. In the third experiment, they were actually able to use, I think it was 3 qubits to cluster graphs with 15, 20 edges, which is pretty impressive, especially considering they did all this with simulations. They didn't actually use quantum computers to run these algorithms. And the fourth experiment showed that these small quantum neural networks could actually model graph isomorphisms. And one of the surprising things they found was that it doesn't take very many qubits to actually model graph isomorphisms thanks to the superpositions of their qubits they were using, and the fact that they were able to essentially fit all of these using a physical system's tendency to decrease the overall energy. They were able to exploit a natural property of not only quantum systems, but physical systems themselves in order to fit these algorithms, which is something I find very impressive. And the conclusions they found from this paper is that quantum graph neural networks can be used to solve a variety of problems. And they also showed that their architectures were flexible and that they could design special quantum graph neural networks by simply abstracting over the edges and using an arbitrary amount of quantum computing power, however much they wanted, to represent these systems. And even with the small systems they used in their experiments in order to test it, by the way, they did this to decrease the amount of time and computing power they needed for completing their experiments, because if they had used more than, I think, 5 qubits, the time to conduct these simulations would have exploded and become unmanageable. But even with the very small and simulated quantum experiments they did, they showed that their models could solve a variety of problems and the architectures were flexible. And they also showed that you could actually use a quantum variational circuit and fit it to a quantum problem by using the inherent energy inside that state. And that the energy of the system mapped directly to the problem they were trying to solve. So as the total energy of the Hamiltonian in their quantum system went down, and all these problems, they were able to fit to all these results, which I find to be the most important takeaway from this paper. So that's my presentation. You guys have any questions?
Good presentations.
Yes.
Julia, do you have any questions?
Yeah, I like sorry, I liked your presentation. Yeah, I wrote down some few questions. I want to worry Adam with some few questions.
All right,
So
ask away.
yeah, I enjoyed it. The first thing I just want to find out is, please, is this graph the same graph as you plotting data points on a graph? Is it that same idea of a graph, or this is a bit
Oh,
different?
this is a completely different graph. This is used to model networks. Basically, you can have a node that's connected to other nodes with edges. It's a graph that looks more like this one here, this one down here.
Okay.
You can, it's a different kind of graph.
Okay, so meaning that, sorry to cut you. So meaning that when you feed in the data into the neural network, then it
Mhm.
transforms it to this graph nature. Is that the whole idea?
Pretty much, yeah. The whole idea is to take graphs like this one and
Okay.
use quantum and use a networked quantum system to model this. They're basically modeling a graph using a quantum graph.
Oh, okay, okay. So meaning that the data we are looking at, that is it here. This is a type of data the neural network is working with.
Yeah,
It's
this is a completely different data type
Oh,
uh,
okay.
than graphs that are placed, for example, on statistics. They're a
Okay.
they're a computer science and math, or they're a
Behind
data
it.
structure based on a formalized definition of networks. You can
Oh,
represent all kinds of networks using these graphs. You can
oh,
represent the internet itself using these graphs.
wow.
Yeah,
Okay, sure.
you can also represent social networks of people between graphs. In fact, that's how researchers were able to learn that each person is only separated by at most 6 connections from every other person. They found that
Okay.
metric by linking, I think it was 10 million people together
Mhm.
using where each person was a node and
Okay,
knowledge of between people was represented as a link.
okay.
Uh, and they were able to find out using the graph that constructed out of that every person is separated by at most 6 degrees from every other person. There's a
That's
joke
good.
in the field that that's 6 degrees of Kevin Bacon,
Oh, okay, sure.
meaning if you hops like if say for example you were in that network and you had all your friends in that network too, along
Mhm.
with the rest of the humanity, you'd basically be
Yeah.
able to go from you to your friend to your friend's friend 3 more
Yes.
times, and you'd be able to get to Kevin Bacon no matter which direction you took.
Yes. That's so
Uh,
true.
and the graphs can model so much more. They're a pretty nifty data structure and a pretty nifty mathematical abstraction, if you ask me.
Oh, okay. So, thank you. I have other questions, but maybe after you've asked, after the others have asked, then I can ask.
All right.
Sure.
Anyone else have any other questions they want to ask me?
Jack, do you have any questions?
Well, I'm sorry that I missed your presentation. I was too caught up with other assignments. I have like 5 things due today, so I'm definitely gonna go back and watch this.
Yeah, that
I don't,
happens.
Okay.
yeah,
That's
so I
okay.
don't, so I don't have any questions at the moment, but I might have to talk to you sometime in the tutoring center about it. So, but yeah, I'm hoping to watch this back because I was pretty excited for you to talk, Adam, but I totally spaced it. So
Yeah, thank
It
you.
happens. It happens to the best of us.
yeah,
Oh,
so
A-
sorry
Adam,
about that.
Yeah.
Oh, Adam, I think this is a complicated paper, and you try to explain some very difficult concept, but
Yeah.
it's very good. Also, I like your section to introduce the background. I think this is important for the reader who has no previous background on that.
Well, the papers certainly didn't bother with the background. It's funny, their entire paper is 7 pages long, and the background is only like 1 page.
Yeah.
Oh,
Oh, I have a questions. In some classical graph neural network, the input usually is one adjacency metric and one feature metric. So I'm curious, in this paper, how do they encode the data to represent a graph? Specifically, how to represent a node and edge here?
Oh, well, each node they used in their quantum graph neural network was represented by essentially they represented a graph with a graph, essentially. That's what they did.
Oh,
And in this, what they called a network quantum system, which is what they defined as the base where they then defined all their other quantum architectures. They built a system where you could have a node and the energy between these nodes and the quantum system is representing the links between edges in the data that they're learning.
Oh,
Basically, the quantum variational circuit, they call it onsats in the paper, is
It's
a graph
confusing word.
itself. It's a graph that's learning from a graph.
oh, okay. I see. That sounds interesting. That's very
Yeah.
quite
It-
different.
Do you think you could put Adam like how did you say it? Ansatz?
Onsats, it's a French word.
Ansatz. Can you give like a definition in your own words of what it is? Because I see that word pop up and I have like a very loose.
Oh, that in my brain is essentially a definition of any quantum circuit.
Okay. Definition.
Just any quantum circuit on a quantum computer that you can get the
Gotcha.
results out of,
Huh.
whether it's variational or not.
Okay, but it is scoped to quantum mechanics or anything.
Mhm.
Okay,
It's
Gotcha.
that word I think is a quantum mechanical word.
gotcha. Okay.
Yeah. I think when I saw it in during my presentation, I think it's like a parameter.
Hmm.
It represents some form of a parameter to achieve maybe accuracy with your model, something of that sort. Yeah.
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 So I said to ask, like, in training this neural network, is it time consuming as compared to other
So
neural networks? Yes.
I
Did they speak about?
imagine it is
Okay.
because it doesn't help in their paper that they didn't actually get access to a physical quantum computer they could test this on, so they had to do it using simulations on classical computers.
hmm.
Oh, okay.
And the
Okay.
simulations, especially for simulating energy in a quantum system, requires storing a lot of state.
Oh, okay.
An absolutely ungodly amount of state, which can balloon up to become huge in size. I asked a professor who works at the University of Utah why she chose to model classical systems in her scientific work over quantum systems, and she said, because the classical systems only take a lot of compute power. They don't take a lot of compute power and memory. She said
Right.
her
Uh-huh.
simulations would consume literal terabytes of memory if you simulated the energy dynamics of quantum systems.
Oh, okay.
That's crazy.
They're huge. And that was a necessary part of this paper because in order to get their quantum variational circuit to learn this, they represented the edges between their data using the energy state of their quantum network.
Okay.
And the quantum network would learn that data by decreasing the amount of overall energy inside that system. So in other words, they had to simulate quantum energy dynamics. That was a necessary part of their model. It wouldn't work without it.
And then he's like, this other thing, I'm just not
I
sure.
see.
And how about the
Thanks
size
for
of the data set? Oh, sorry.
Oh, the size of the data sets was pretty small. Most of the graphs they were using on the third and fourth experiments had, I think, 10 nodes and 15 to 20 edges. The reason this was all synthetic data too. The reason they did that was because they wanted to show that their algorithm would work in a simulation. Basically, they wanted to show that their quantum graph neural networks would work at all. And they wanted results back in days rather than months. So they chose our
Okay.
very small synthetic data.
A small size. Okay.
Yeah.
Thank you.
Yeah, thank you, Adam.
You
Yeah,
guys have
it's
any
a
other
very good
questions?
presentation.
Yeah.
Well, good.
I think I was just curious to ask about the time series data they considered, because I feel it to be a whole difficult something. I don't know. Like you mentioned some time series data in your presentation somewhere.
Where was
Yeah.
it? First experiment, conclusions, time-dependent quantum dynamics. Hold up. I'm gonna go actually get the paper real quick.
Okay. But I'm just being curious though, I'm just being curious.
Yeah, this is the paper itself. This is it itself isn't very long, but yeah, this is the math behind it right
Okay.
here. This is why I said that they didn't go properly into detail with the background, because they just like show the math equations and they don't really talk
Yeah.
about examples.
Is
And
that
they
Whatever
also,
it is.
this is for the graph?
yeah,
Graphs. Oh, I see.
this is the math classical computers use to learn graph data, namely convolutional networks.
Okay.
Yeah,
Okay.
this is too short. Maybe difficult for some reader with no related background.
Yeah, this is meant for people who have
Yes,
background in the
yes,
subject.
yes.
And this is the actual math behind their quantum graph neural network.
Okay.
And the trainable parameters are stored in the Hamiltonian. They're, in other
Mm.
words, the energy state of their network quantum system.
Okay. Wow. You did a great job.
Yeah, this is some really dense
It's so
reading.
complex, crazy.
Yeah, where was the actual experiment they did for their learning quantum Hamiltonian dynamics? Okay, they basically used their quantum system to represent like a simpler version of itself.
What?
Yeah, they pretty much used their own neural network to model itself. Yeah, they did that.
Hmm.
They went full meta here.
Interesting. Let's see.
This was a time series dependent data, and I think what they did was to learn the target Hamiltonian parameters, state evolving. They basically trained this thing over time steps.
Okay.
The data we're looking at here is data that they gathered as the model learned based on like time step 1, 2, 3, 4.
Okay. 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 I get it. Yeah. It makes sense.
Yeah.
Thank you. Yeah. Thank you.
Yes, thank you.